Ever wondered how AI theory and coding intersect? In today's discussion, you'll find out. AI, or artificial intelligence, is a fascinating field that combines theoretical knowledge with practical coding skills. Understanding the theory behind AI is just as important as knowing how to code. It's akin to learning the theory of flight before piloting an airplane. This symbiotic relationship between theory and practice allows us to create intelligent systems that can learn, adapt, and make decisions. In this video, we'll unravel the secrets of AI theory, delve into the coding basics for AI, explore regression and gradient descent, examine classification algorithms and metrics, and introduce you to the world of deep learning and neural networks. We'll also address some common challenges in AI coding and share best practices. So, are you ready to dive in? Let's explore the intriguing world of AI. To understand AI, we first need to grasp its fundamental concepts. At the heart of AI theory are three key pillars: machine learning, neural networks, and algorithms. Machine learning, in essence, is the process by which computers learn from data without being explicitly programmed. It's akin to how we humans learn from our experiences. Algorithms, the step-by-step procedures for calculations, are the building blocks of machine learning. They guide the computer in its learning process, helping it make sense of the data it's presented with. Neural networks take inspiration from our own brains. They consist of interconnected nodes, or neurons, and they're capable of learning and improving over time. Just as our brains strengthen certain connections based on our experiences, neural networks adjust their connections based on the data they process. But what do these networks learn from? This is where supervised and unsupervised learning come in. In supervised learning, the machine is given data along with correct answers. It's like a teacher guiding a student. The machine learns to predict outcomes based on this guidance. On the other hand, in unsupervised learning, the machine is given data but no explicit instructions. It's left to find patterns and relationships on its own, much like a child exploring a new playground. Now let's talk about regression and classification. Regression is used when we want to predict a continuous outcome, like the price of a house based on its features. Classification, on the other hand, is used when we want to categorize data into different groups, like identifying whether an email is spam or not. And we can't discuss AI theory without mentioning the mathematical foundations that it stands on: linear algebra, calculus, and statistics. Linear algebra allows us to work with multidimensional data, calculus helps us optimize our models, and statistics provides us with the tools to make sense of the data we're working with. Remember, understanding these fundamentals is key to unlocking the power of AI. It's like learning to read music before playing an instrument. You can pluck strings and create sound without knowing how to read music. But to create a symphony, you need to understand the notes, the scales, and the rhythm. With the fundamentals under your belt, it's time to delve into the practical side, coding. Because at the end of the day, it's the combination of theory and coding that turns the abstract concepts of AI into tangible, real-world applications. Coding is the tool that brings AI theory to life. Imagine AI theory as the blueprint of a grand building. Coding is the bricks, cement, and steel that actualize the blueprint into a tangible structure. The languages of Python, R, and Julia are the essential elements in our coding toolkit for AI. Python, known for its simplicity and readability, is a favorite among many AI enthusiasts. It's like the friendly neighbor who is always ready to lend a helping hand. Python offers a vast range of libraries specifically designed for AI, such as TensorFlow and Keras, making it a go-to language for beginners and experts alike. Next, we have R. It's like the wise professor who knows all the statistics. R is a powerful language for statistical computing and graphics, making it an excellent tool for data analysis and machine learning. Its rich ecosystem of packages like Keras and MLR help in creating robust machine learning models. Then, there's Julia. It's like the young prodigy who is fast and efficient. Julia combines the ease of Python and R with the speed of languages like C, making it perfect for high-performance numerical analysis, a key aspect in AI. Now let's talk about some helpful friends, the libraries. Libraries and coding are like the helpful elves in a workshop, making your life easier by providing pre-written codes for common tasks. In Python, for instance, we have NumPy and Pandas. NumPy, or numerical Python, is the backbone of numerical computation in Python. It's like the powerlifter in the gym, handling large data arrays and matrices with ease. Pandas, on the other hand, is the meticulous organizer. It offers flexible data structures, making it easier to work with structured data. And then we have scikit-learn, the versatile all-rounder. It provides simple and efficient tools for data mining and data analysis, making it an essential part of the Python machine learning toolkit. But before we can start building, we need to set up our workshop, or in this case, our development environment. Think of it as the canvas where you'll paint your AI masterpiece. You can use platforms like Jupyter Notebook, Google Colab, or Anaconda. They come with many useful libraries pre-installed and provide an interactive coding experience, ideal for AI coding. Setting up these environments is like assembling your toolbox. You download and install the platform, load up necessary libraries, and voila, you're ready to start coding. Remember, every successful AI project is a symphony of theory and coding. It's about understanding the problem, knowing the theory, and translating it into code. It's about iterating, debugging, and learning from each step. Now that you're set up, let's put theory into practice. Regression models and gradient descent are key to understanding AI coding. Let's start with regression models. In the realm of machine learning, regression models are used to predict a continuous outcome. Think of it like this. You're trying to predict the temperature for tomorrow based on historical weather data. That's where a regression model would come in handy. There are two main types of regression models, linear and multiple. Linear regression is the simplest form where we predict the outcome based on one independent variable. For example, predicting a person's weight based on their height. On the other hand, multiple regression takes into account more than one independent variable. So in multiple regression, we could predict a person's weight based on their height, age, and diet. Now let's talk about the mighty gradient descent. It's an optimization algorithm that's used to minimize the error function or the cost function in machine learning models. The goal here is to find the best parameters for our model that results in the smallest possible error. Imagine standing at the top of a hill and you want to get down to the base. You would likely take steps in the direction where the slope is steepest. That's what gradient descent does. It iteratively adjusts the parameters of our model, taking steps proportional to the negative of the gradient, or descent if you will, to reach the lowest point, which represents our minimum error or cost. Now let's get our hands dirty with some coding. Today we'll code a simple linear regression from scratch using Python. Don't worry, it's not as intimidating as it sounds. First, we'll import our libraries. We'll need NumPy for mathematical operations and Matplotlib for plotting our regression line and data points. Next, we'll create our data. For simplicity, let's create an array of 10 numbers for our independent variable x. Correspondingly, we'll create an array for our dependent variable y. Now comes the fun part, creating our linear regression model. We'll start by calculating the mean of x and y, then we'll calculate the deviations of each x and y from their mean. We multiply these deviations together, sum them all up, and divide by the sum of squares of deviation of each x. This gives us the slope of our regression line. To find the intercept, we subtract the product of the slope and mean of x from the mean of y. Finally, we'll plot our data points and the regression line. And voila, we've just created a simple linear regression model from scratch. Remember, this is a very basic representation. Real-world data would require a more complex approach and additional steps like data cleaning, feature selection, and dealing with outliers. With regression under your belt, let's explore another critical aspect, classification. Classification algorithms are essential in making predictions with AI. They form a cornerstone of machine learning, helping us to categorize data into specific groups or classes. They're the key to everything from email spam filters to facial recognition and even medical diagnoses. Let's start with logistic regression. Despite the name, logistic regression is a classification method, not a regression technique. It's used when the response variable is categorical. For instance, it can predict whether an email is spam or not, or if a transaction is fraudulent. In essence, it estimates the likelihood that an instance belongs to a particular class. Next up is k-nearest neighbors, or KNN. It's a simple, intuitive algorithm that classifies a data point based on the majority class of its k-nearest neighbors. Think of it as a popularity contest among data points. The more neighbors you have from a certain class, the more likely you are to be part of that class. Then there's naive Bayes. It's a powerful algorithm based on Bayes' theorem with an assumption of independence among predictors. It's naive because it assumes the presence of a particular feature in a class is unrelated to the presence of any other feature. It's particularly suitable for large datasets, and despite its simplicity, it can outperform more complex models. But how do we measure the performance of these algorithms? That's where evaluation metrics come in. Accuracy is the most intuitive metric. It's simply the proportion of correct predictions. But accuracy can be misleading, especially for imbalanced datasets. Precision, recall, and the F1 score provide a more nuanced picture of an algorithm's performance. Precision is about how accurate your positive predictions are, while recall, also known as sensitivity, measures how many actual positives your model catches. The F1 score is the harmonic mean of precision and recall, giving us a single metric that balances the two. To bring it all together, we can implement a logistic regression classifier without relying on libraries. This hands-on approach deepens our understanding of the underlying workings of the algorithm and allows us to customize it to our specific needs. Now, it's time to go deeper with deep learning and neural networks. Deep learning represents the cutting edge of AI theory and coding. It is a subfield of machine learning that uses algorithms inspired by the structure and function of the brain's neural networks. In essence, a neural network is a series of algorithms that endeavors to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. The most basic unit of a neural network is the perceptron, which takes several binary inputs and produces one binary output. To understand neural networks, we need to delve into the concept of activation functions and layers. Activation functions are mathematical equations that determine the output of a neural network. They help decide whether a neuron should be activated or not. Some common activation functions include the sigmoid, tan, and ReLU. Layers, on the other hand, are like building blocks of a neural network. There are three types of layers: the input layer, hidden layers, and the output layer. The input layer receives the raw input, the hidden layers perform computations, and the output layer produces the final result. Coding a basic feed-forward neural network can be quite straightforward, especially with libraries such as NumPy. NumPy is a library for the Python programming language, adding support for large multidimensional arrays and matrices, along with a large collection of high-level mathematical functions to operate on these arrays. In the world of deep learning, backpropagation is a key concept. It is an algorithm used for training neural networks. Backpropagation calculates the gradient of the loss function with respect to the weights of the network for a single input-output example, and does so efficiently, unlike a naive direct computation. This makes it possible to use gradient methods for training multi-layer networks, updating weights to minimize loss. As we near the end, let's discuss some challenges and best practices in AI coding. AI coding isn't without its challenges, but knowing the best practices can help. One common hurdle is overfitting, where your model performs superbly on training data but poorly on unseen data. This typically results from an overly complex model that's too attuned to the training set. Regularization techniques can help mitigate this. Another challenge is hyperparameter tuning. Selecting optimal parameters for your AI model can be like looking for a needle in a haystack. Grid search and random search are common strategies to tackle this task. Then there's the crucial importance of cross-validation and model evaluation. Splitting your data into separate training and testing sets can give you a better idea of how your model will perform in the real world. And using metrics like accuracy, precision, and recall can provide a well-rounded view of your model's performance. Above all, never stop learning and exploring. AI is a rapidly evolving field, and staying up to date is key. Armed with these insights, you're well on your way to mastering AI theory and coding. We've covered a lot of ground today, from theory to coding. We've delved into the fascinating world of AI, exploring the interplay of theory and practical application. We've discussed the foundations of AI, from machine learning and neural networks to the critical algorithms that make them tick. We've also touched on the coding basics, highlighting the key languages and libraries that are instrumental in AI development. We journeyed through the realms of regression and gradient descent, classification algorithms and metrics, and the enthralling world of deep learning and neural networks. We also addressed the challenges you might face and the best practices that can guide you through your AI journey. This symbiotic relationship between theory and coding is the core of AI, each feeding into and enhancing the other. Remember, mastering AI theory and coding opens doors to exciting possibilities. Keep exploring, keep coding, and see where AI can take you.